So following on from last week, just give me 50 minutes. We learnt last week about the different types of loads we need to consider: dead, live, wind, earthquake. We're limiting ourselves to dead and live loads. We learned how when we design a structure, we just don't design it for strength. We design it for serviceability, that is deflection. If it was a sports floor, you would ensure vibration as well. You would do a vibration check, because we don't expect vibration problems in a room like this. You wouldn't do a vibration check. But strength and deflection. So we have two things we have to check. And we also learnt when we put the loading on, we don't put average loads on, we put extreme loads on, because the consequences of something failing are extreme. Okay, are fatalities. So we put extreme loads on. And we use the same dead and live loads, however we use different load factors. So for ultimate limit state, okay, for strength here, ultimate limit state, you would use the greater load factors. For serviceability, deflection checks, you would use the smaller load factors. And when we do those two completely independent designs that you don't know how to do yet, but when you come to do them, you give them equal weighting, equal importance. Okay? So you don't say, oh, I'm just a bit higher than the deflection I need to be, but it doesn't matter, it's only deflection. You can't say that. Okay? You have to treat deflection just as significant as failure when you come to do that. So what do we know? What are we doing next now? Okay, today or this week, I've introduced to you the idealised loads, point loads, uniformly distributed loads, moments. We'll talk about the different types of idealised supports we have for our structures. We'll just briefly cover consideration, stability. Then we'll go over how we calculate these forces, reactions using equilibrium and free body diagrams. We'll formulate our equilibrium equations and solve for reactions in structures. So, if you haven't done physics, this is not difficult, but you may need to just concentrate a little bit harder. So, last week I mentioned, I told you that we idealise our loading in three ways, either as being a point load, a uniformly distributed load, or a blanket load. So if this was a system in 3D, if we were working in 3D, then our loading would be applied everywhere, and that would be a load in terms of kilonewton per metre squared. But generally with this subject, we're dealing in 2 dimensions. So we'll work in kilonewtons per metre, kilonewtons, or an applied moment. And remember, the units of moment here, a kilonewton metre, force times distance. So, we have 3 types of supports, our mathematical models, our support models. We have what we call a fixed support, a pinned or simple support, and a roller support. And I'll go through those 3 in more detail now. So, a fixed support. A fixed support is where the member can't translate or rotate at the support. So the support provides reactions to prevent that translation and rotation. In 2 dimensions, a fixed support has 3 potential unknown reactions: a moment reaction and 2 force reactions. So my triangular ruler here, that would be me grabbing this with my fist. I can't pull up, I can't push sideways, and I can't rotate. When I try and rotate, my fist applies an opposing, the support applies an opposing rotation to any forces on the system. So the image you see here, that is the base of the footbridge going over Blackburn Road, that truss footbridge. If you ever want to stop and have a look at the base, you can see it's a nice thick plate here, and it has 12 bolts in there holding the column, support column to the bridge very securely to the concrete base. If you were dealing with a steel column joining onto a steel column, to get that to assume a fixed connection, you would have to have connections here at the web level, at the flange level, and at the web. and at the lower flange here. So there's no relative rotation. So no relative rotation is allowed between the column and the beam. Okay, so for a fixed rotation, just want to confirm when I say there's no rotation, what that looks like. So what that means is there is zero rotation where the member comes out of the support. So this is very important when you come into second year as well, that you understand that. So here you have a beam with two fixed ends, and here you have a cantilever beam. And in each case here you can see when you look at the actual slope, there's no slope change at that support point. So that's a fixed member, and we draw it as shown. We draw it as a wall with dashed lines indicating concrete or brickwork or something solid. Our next support type is what we call a pin or a simple support. Here we have the base of the Sydney Harbour Bridge. So effectively we have a hole in our arch bridge here, and we have a support point, and we slot the two members in and we slide a pin into the joint. So a pin is like a door hinge. So the member can't translate, but it can rotate at the support. So the support now provides reactions to prevent translation only. So in 2 dimensions, we have two potential unknown forces, an Fy and an Fx. And we draw a pin connection as a triangle. So a pin connection is me now grabbing my ruler just with 2 fingers. So I can't pull down at that point, and I can't pull sideways, but you can see there's rotation allowed now. So that's as compared to the fixed, where when I tried to rotate, I couldn't rotate. So that's a pin connection, and that's a fixed connection. So 3 unknown reactions at a fixed, 2 unknown translational reactions at a pin. Our third type of support, a pin connection. Going back, here are some common pin connection supports here. When you have 2 beams connected just by a single cleat plate. Here in the engineering car park, because the flange down here hasn't been secured firmly to the column. Let me just change colours there for a minute. Because there is no connection plate in here doing that, connecting it rigidly, then that is a pin connection. You may come to me and say, Lizzie, my goodness, when you have 1, 2, 4, 6, 8, 10 bolts in there like that, there's no relative rotation allowed between the two. As long as some rotation is possible, we then have to idealise. We have to say, well, if some's possible, it immediately becomes a pin. So in reality, it's part of the way between fixed and pinned. But in our modelling, we have to always err to the less conservative, so that would become a pin connection. So you may say here also, there's some fixity here. We have 4 bolts in here. Because it's not fully rigid, we assume it to be, we take it to be a pin. We idealise it as a pin. So when it comes to a pin connection, there now is rotation at the support. The final support type is a roller support, and this one doesn't occur that often. An example of a roller support is an elastomeric bridge bearing. So if anyone rides along the Gardeners Creek Trail, and you go under the southeastern freeway there next to St. Kevin's and whatever else is there, you'll see, it's great, you can see all the bearing pads there. All the rubberised bearing pads supporting the bridge. Now what these bearing pads do is they allow no vertical movement, but they actually shear quite a bit. So they allow sideways movement, and they also allow rotation. So that would be an idealised example of a bearing pad is a roller support. So a roller support restrains only in one direction. So we only have one unknown now. And a roller support is me now grabbing my ruler with my 2 fingers. So I can now push it sideways. I can now rotate, but in terms of movement down, I can't push down. So please be clear that a roller support, it's drawn like that. People think, oh, it can flip up. A roller support restrains in the positive and negative direction, okay? No upwards in this case, sideways allowed, rotation. You can have roller supports, horizontal rollers here, or you can actually have vertical rollers as well. And that would be me holding my ruler like that. Or in actual fact, if I have a ladder, which we'll have later, leaning against a wall. So it can move up and down, okay, but it can't move sideways. So there are our three support types. Once again, I just want to be clear you understand the difference in terms of what the deflected shape looks like. So we have pin and roller supports here, which allow rotation at the support. So we have rotation here as compared to fixed supports where there's no rotation at all. So here are now our three idealised support types. Fixed, pin, roller, line with dashes, triangle, circle. Three possible unknown forces. One of them may be zero, two of them may be zero, but three unknowns. At a pin support, two unknowns, and at a roller, one unknown. So, again, in reality, you can't look at a support and go, that's definitely a pin, that's definitely a roller. Okay, we're idealising this. The most commonly used structural element is a simply supported beam. You'll see in the examples you do next week a lot of simply supported beams. One end is drawn as a triangle and one end is a circle, so we have a pin and a roller support. So we idealise it mathematically as a pin and a roller support. In reality, both supports are usually the same. They look the same. If you come and look at these connections up here, these end connections of these beams up here, or you go into the engineering car park and you look at all the beams, you'll see, well, the two connections look the same. So in reality, both supports are the same. They're neither a true theoretical pin or a roller. As long as some horizontal movement to allow temperature expansion and contraction is allowed, we theoretically define the supports as being a pin and a roller. So there are three support types. Just a few words on stability. This mightn't be in your notes. Don't worry, there's not a lot here. When I add extra, it's because I want to improve things. If I have added any that aren't in the original you've printed off, then when I save the ink-ins online, I'll put these in there as well. So the main task of a structural engineer is, of course, to design a stable structure. Stable structures have adequate restraints and reactions to prevent them from rotating and translating. Stable structures are in equilibrium, unstable structures will collapse. So here to the right here, in order for my cantilever to be stable, my fixed support here, I have three possible reactions. If there is a pin here, if we have this shown as a pin here, then we only have two possible reactions, and that's unstable because with that load on, this thing will actually collapse down. In terms of a simply supported beam, well, we need to mathematically define one end to be a pin and one end to be a roller, because if both ends are simply rollers, we have no sideways stability. Okay, that would mean this thing could move to the side. Gust of wind blowing, any sort of sideways force, be it impact loading from a car or an accident or anything, it would move sideways. So the minimum restraint you need is a roller and a pin and a fixed support if it's a cantilever. Okay, so we know all about structural forms, beams and trusses, what they look like. We know a bit about loading now, and we know that a structure has to be stable. What we're going to do now is we're going to firstly calculate reactions and then internal member forces. So we're going to focus on reactions this week. What's the next step? Before you can calculate deflections or any internal stresses, the first thing you have to do is calculate reaction forces. And to do that, we use equilibrium and free body diagrams. So you all know what equilibrium is, regardless of whether you did physics or not. It's the most important concept in structural engineering. The Oxford Dictionary, when I looked it up, defined it as a state of balance. And we know forces must balance. Why? Well, Newton's third law. Every action has an equal and opposite reaction. So you are currently sitting in your chair, you are currently applying a downwards force, and because you're not falling over and the chair's not collapsing, that means there is an opposing force up. So you are in a state of equilibrium. The sign convention we're going to work with is the standard Cartesian coordinates. To the right is positive, up is positive, and anti-clockwise is positive. Anti-clockwise is positive based on the right-hand screw rule. If you've never met it before, you point your thumb in the direction of the axis, your right hand, and the way your fingers curl will define what's positive. So I have the x, y, z coordinate here, axis here. So that's the way x, y, z go. I point my thumb in the direction of z, and can you see my fingers curl anti-clockwise? So that what defines my moment as anti-clockwise is positive. So whenever you have a situation where you calculate your reactions, always draw them, I suggest you always draw them positive to the sign convention, and when they work out to be negative, you know, a negative horizontal force means it's going to the left, a negative vertical force means down, a negative moment means it's clockwise, not anti-clockwise. It's a good habit to get into. Okay, equilibrium. We're dealing in 2D, so we have three equations of equilibrium. All the forces in the x direction must equal 0, all the forces in the y direction equal 0, and all the moments about the z-axis, because z here is coming out of the page, must equal 0, because we want our structure to be stable and in equilibrium. If we were working in 3D, which we do in second year, you then will have 6 equations of equilibrium. But we're only going to be working in 2 dimensions, so we have 3 equations. So how many unknowns can we solve for? 3 equations, 3 unknowns. Okay? You know simultaneous equations, 2 unknowns, 2 equations, 3 unknowns, 3 equations. So in order to calculate reactions, our structure can have no more than 3 unknowns in it. So when we look at equilibrium, well, in the y direction, we have to ensure that, in this case here, with our crane, the forces down, the weight of whatever the crane's carrying and the counterweight have to be equivalent to the load up at the support. So you would ensure the ground the crane was connected to could handle that level of load. Horizontally, when you have your wind blowing, okay, again, it's not enough just to sit your crane on the ground. You would have to key it in somehow to be able to restrain any horizontal movement. And the one people find the most difficult is your overturning moments. It's not enough just to balance it there. Your support here, you have to have enough moment at the base in order to counteract any moment from your loading. So rotational equilibrium, what is a moment? Okay, a moment is a force times a distance. In order to sum all the moments, because it's a force times a distance, you have to define at which point you will take moments. So you have to define your datum point. And when you do take moments, very importantly, a moment is not just a force times a distance, it's a force times the perpendicular distance to the force. Okay, so it's perpendicular distance. So in this case here on the left-hand side, taking moments at A, okay, our moment would be F times our lever arm. On the right-hand side, our lever arm here is perpendicular now to the direction of the load. So this lever arm here forms a right-angled triangle. The distance we're talking about forms a right-angled triangle to the moment. If your force is horizontal, your distance is vertical. If your force is vertical, then your distance is horizontal. So remember that. It's a combination of horizontal, vertical, or just perpendicular if your force is at an angle. We'll look at this in more detail. So units of moment, force times distance. Newton metre, kilonewton millimetre. Anti-clockwise is positive. When you have 2 forces in line, They create no moment. They are what we call concurrent. So let's look at some rotational equilibrium. We have a seesaw here. We want the whole thing to be balanced. So I think we all know, taking moments at the centre here, if this x here is 5 metres, in order to get rotational equilibrium, so we have a moment here applied on the right-hand side of 25 kilonewton metres, force times distance, and on the left-hand side we have a value of p times x. So if x is 5 metres, p would be 5 kilonewtons. If x becomes 4, so if the moment on this side now is p times 4, well, that has to equal 25, so you could work out the value of p. So there's nothing terribly difficult about any of this. Before we get into actually looking at beam systems, I want you just to be able to spot whether you have rotational equilibrium or not. So have a look at this system of forces here. In terms of forces in the y direction, we have down to, up to, so we have equilibrium in the y direction. In terms of forces in the x direction, well, we have 5 to the right, 5 to the left. We have equilibrium translationally in the x direction. Do we have moment equilibrium here? No. Let's look at these two forces. These two kilonewton forces, will they create an anti-clockwise moment equal to, if we take moments at point A here, they create a moment of 10 kilonewton metres. Regardless of where you take moments, if we take moments here at B, the moment created is still 10 kilonewton metres, force times distance. If we now consider our horizontal forces of 5 and 5, and because they are 5 metres apart, can you see they create, those two forces as a couple now cause a clockwise moment of 25 kilonewton metres. 2 metres apart. Oh, I've got that wrong, thank you. 2 metres apart. Oh, so who said no? So that's 10 as well. So can you see now, if you sum the moments, you would get 10 minus 10 equals 0. So you have rotational equilibrium there. So my first example, having rotational equilibrium. Now my second example, is this system of forces in equilibrium? I would look at it and say it's in translational y equilibrium. It's now in translational x equilibrium. Can you see the forces balance? Is there moment equilibrium here? Again, we have our 5 kilonewton forces, but this time, what were they last time? They were the 2, being the vertical forces. So there's an overturning moment here of 25. And when we consider our horizontal forces, they are now 2 this time, and that's 2 metres apart. So now we have an overturning clockwise moment of 4. So if we do sum the moments, anti-clockwise is positive, we'll have 25 minus 4. So we have no moment equilibrium in our system. Moment equilibrium. So that means if I would put a big blob in there with those forces on there, that blob wouldn't be moving in space, but it would be rotating. So of course, that's not possible when you have structures. Structures don't move. So you have equilibrium all the time. So based on knowing you have equilibrium, you can then calculate what those forces actually are. So we now know about the structural forms, the loading, the structure stable. We know about support reaction types. And so we're going to calculate our supports. So we've covered equilibrium now. Now I want to introduce you to free body diagrams. So what are free body diagrams? People that have done their tute already today will have covered this, so I'll just cover it again. When we isolate part of a structure, we call it a free body. So in this instance here, I'm isolating the top floor of the building with the man on it. Now the diagram of that part of the structure with all the forces on it, we call a free body diagram. So here's my free body. I turn my man into a force. I turn my roller into an unknown reaction up, because a roller has one possible reaction. I turn my pin into two unknown reactions. This system now is in equilibrium. It is stable. So we have three unknowns. We have three equations of equilibrium, so we can solve for our equations, our reactions. So just be aware, when we create our free body diagram, it has a closed loop boundary. It's a circular loop. We draw a circle around an area and we pull everything in that area out, in that circle out. So the forces on a free body diagram include all the applied forces and all the reactions, and the forces on a free body diagram of a stable structure are in equilibrium, so we can solve. So we use free body diagrams in equilibrium to calculate reactions as well as internal member forces. We'll do that in the coming weeks. This week it's all about reactions. So in this example here we have a ladder lying against a wall. The wall is smooth, the ground is rough. Can you imagine what that free body diagram looks like? Well, our ladder is a stick. Up here at the wall we said it was smooth, so that means there would be no restraint, no friction, so no force in the y direction, hence only an x reaction here. The connection between the ladder and the ground is rough, so we can rely on friction down here, so we have two possible reactions, and we have the weight of our ladder. So knowing the weight of the ladder, we can now calculate what the reactions are on that ladder. A more simple example, a sphere hanging from a ceiling. Okay, we want to know what the force is in the cable. We just draw our closed loop boundary around it. We know the weight of our sphere, of our light shade or whatever it is hanging from the ceiling. We can work out the force in the cable holding it. And by knowing the force in the cable, we can then design our cable. We want to know what the force is in the roof. Same system. We can draw our free body diagram. We know this force down would be upwards here, is this force down, to have balance, and we can work out our reaction. So again, just take note, when you draw a free body diagram, you draw a loop around everything and you include everything in the loop but nothing more. This will mean something when you come and do it. Okay? So, I think you now realise three unknowns, three equations we can solve, and we call that a determinate structure. In a determinate structure, the reactions can be calculated using only the three equations of equilibrium. So what I'm going to teach you now only applies to determinate structures. If we put extra support in there, we won't be able to calculate the reactions. A determinate structure has only one load path, from an applied load to the support. If I take support A away, this system will fail. If I take support C away, the system would fail. So a determinate structure, three unknown reactions. So here we have an indeterminate structure. We have two roller supports and a pin support. So we have four unknowns. So in an indeterminate structure, the reactions cannot be calculated using only the three equations of equilibrium. The reactions of an indeterminate structure are found by using external displacements as well as equilibrium, and we'll be working on that in about week 11. So up to week 11, everything will be determinate. And in reality, out in the workforce, if it's indeterminate, who cares? You stick it in your computer model and it can calculate all the forces. So when you have a structure, before you look at it, you have to ask yourself, is it stable? Is there restraint in the X, Y and moment restraint? No, the structure has failed. So if I said, okay, I want you to analyse this cantilever beam that has a, well, it's actually has a pin support here, you would say, no, that's unstable. It's going to fall down. So once you decide it is stable, okay, yes, there's a fixed support and a point load, it's stable, is it determinate? If you look at the unknowns and you say, I have 3 unknown reactions, okay, then it's determinate. You can determine those reactions, proceed. If it has any more, no, the reactions can't be calculated using just equilibrium. That's where you would stop. Okay, let's do some examples. I'll start off doing very simple ones and gradually get more difficult. In saying they gradually get more difficult, I'm actually using no different method. If you understand equilibrium and free body diagrams, you can calculate forces in any system. So I'm using the same method for every problem. Okay, simplest beam, I have a man. He weighs 80 kilos, and we now know 80 kilos. We multiply by 10 for gravity, and when we do that, our force will be in newtons, and then we divide by 1,000 to convert to kilonewtons, and that gives us our 0.8 kilonewtons. So we have a man, he's not sitting in the middle of the bridge or the floor. If he was in the middle of the floor, symmetry, the reactions would be the same. So what are the reactions at A and B? Okay, here is my free body diagram. Do I have to think this through? No, you can learn this. But of course I want you to think it through. Let's look at our 3 equations. All the forces in the x direction equal 0. When I drew my reactions here, my unknown reactions, at a pen I drew the 2. Whether they have a value or not, I'll find out now. So in my free body diagram, I say, okay, I have a Bx force, and that's the only force I have in the x direction, so that must equal 0. So therefore, even though I have the potential to apply a horizontal reaction, the horizontal reaction is 0. I use my second equation, all the forces in the y direction equal 0. I have AY plus BY minus my 0.8 equals 0. So I can't work anything out now. I need to use my third equation. So you always have to use your 3 equations. You can't say, I don't like that moment equation, I'm never going to use it. So now we're going to take moments. And it is about the z-axis, because our coordinate system has z pointing out. So that is a moment about the z-axis. So when you take moments, I said you need to define the point at which you're taking moments. Easiest place to take moments is at one of the supports. So let's take moments at support A. And a sum of the moments equals 0. We know that for a fact because our structure is stable. It's not moving, so it must be in equilibrium. So let's take moments at A. What is a moment? A force times a distance. The first force is 0.8. The perpendicular distance is 6 metres. Is that causing a clockwise or anti-clockwise rotation? The way I do it is, good, you stick your finger on A, you apply that force and you say, okay, that 0.8 is causing clockwise rotation. So therefore, that becomes negative. So I don't put the sign in till later. Now, does my Bx cause a moment? My force is Bx. What is the perpendicular distance from A? 0? No, it's 0. Perpendicular distance from A. Bx actually runs through A. So Bx times 0, normally I don't even bother putting that in the equation. Okay? But the reason we leave it out is because we have a force times a 0 perpendicular distance. The final force we have is By. So I don't put the sign in yet. I say By times 10 this time. Does that cause clockwise or anti-clockwise about A? The way it's drawn, anti-clockwise. So that would be plus now. There, all that we've got there. So from that, By equals 0. Oh, not 0, what am I saying? 0.48 kilonewtons. And then subbing into equation 1, you get AY is equal to 0.32 kilonewtons. And then you ask yourself, oh, would I expect B to be bigger than A? The load is applied closer to support B. So yes, you would expect B to be the bigger reactive force. So far so good? Okay. Let's now have our man sitting on the floor, and now we're including the weight of the floor. So it's actually a beam, it's not a floor. We have a beam here. In terms of the cross-sectional area, here is my cross-section. It's 0.1 metres wide. It's 0.2 metres deep. So if I cut through, draw a line, and I put 2 arrows on it, and I call that section AA, that means if I cut through my beam and look in the direction of the arrows, this is what I would see. A beam that's 0.1 by 0.2. Now when I do these examples, I'm not putting load factors and everything on now, okay? When you do the problems, when you get given them in the class next week, assume those loads are characteristic loads with the appropriate load factors. Okay, so our free body diagram now, we have a point load representing the weight of the man, and now we have a uniformly distributed load. So, how much does our beam weigh? To work out the weight of the beam, kilonewton per metre of the beam, the area of the beam was 0.1 times 0.2. And last week I said if you get the cross-sectional area and you multiply it by density, so this beam is concrete. If you look at your units here, area is metres squared, density 24 kilonewtons per metre cubed. That will give you a weight of beam, 0.84 kilonewtons per metre. If you're sitting there right now saying, why did she multiply that by that? Let's do it the long way, but who cares? That total beam weighs volume times density divided by length. So the volume is my area times my length. My density is 24. That number on the top there now is in kilonewtons. We want to know what the load is in kilonewtons per metre, so we divide by 10 metres. So as you can see, the 10s cancel out, and you have a load of 0.48 kilonewton per metre. So this W force now, 0.48 kilonewtons per metre. So, let's work out our 3 equations now. All the forces in the x direction equal 0, based on our free body diagram. In the x direction, all we have is a bx force, and as that's the only force, once again it must equal 0. Now we go to the y direction. So we have our 2 upward reactive forces, AY, BY. We take away our point load, and now we take away the total uniformly distributed load is 0.48 kilonewtons per metre, and it's acting over 10 metres. So there is a downwards force here. Now, I'll draw it as a squiggly line. That's our equivalent load now here is 0.48 times 10 metres. So we have the weight of the floor weighs 4.8 kilonewtons. And And all of that, once again, equals 0. So we come to take moments again. Taking moments, let's take moments at A again, at support A. So again, our moment, we have 0.8 times 6 metres. That's going clockwise, can you see that? So that's negative. Now, when we take this equivalent point load, where does it act? Well, if it's symmetrical, we know the equivalent point load always acts in the middle. So this distance in here, excuse me. So that distance in here, if we assume it's acting in the middle, is 5 metres. So now I consider my force, my equivalent weight, load is 4.8 kilonewtons per metre, kilonewtons now, and it's acting in the middle, so times 5 metres. That's also causing clockwise rotation, so that's negative. And once again, I just have my By times 10. I won't include that Bx force because you can see if you trace that arrow back, if it runs through the point, it causes no moment. So that's plus. From that, we get a value for By. And then if I call this equation 1 and then sub into 1, gives you an AY value of 2.72 kilonewtons. Now, a good thing to do at this point would be to double check yourself. If you think, oh, I'm always prone to mistakes, what I will do now is I'm going to now take moments. Oh, why can't I write up there? Eraser. What I'm going to do now is I'm going to take moments at B. Oh, damn, excuse that, that won't work out. If you take moments at B, so there's an exercise for you to do at home. I want you to take moments at B using those reactions you've calculated, and taking moments at B, if it doesn't add up to 0, you have made a mistake. So you can check yourself always. You can walk out of the test and the exam saying, I got it right, I know I got it right because I checked myself. So if we take moments at B, have a look, we're now taking moments about B. The moment 0.8 times 4, is it positive or negative? Is it going clockwise or anti-clockwise? It's now going anti-clockwise, so it becomes positive. Okay? The weight of the beam itself, that's also going anti-clockwise, so that's positive. And our AY now causes clockwise. So your moment changes sign as a function of where you take moments about. Okay, so you're thinking that's all easy peasy. We'll do one more. We've got 5 minutes. Yes, it's got a moment on it. But if you understand equilibrium, it is no harder than before. We draw an AY force at our roller. Always draw your unknowns positive to your sign convention. Bx, By. 3 unknowns. So, have a look now. I know it's got an upstand on it. Ignore the upstand. That moment means without supports, this beam would be rotating like so in space. Okay, say it was weightless and it just had a moment, it would be rotating like so. So the reaction at AY, is it up or down to stop that from happening? I would be pushing up to stop that from happening. The reaction at B, is it pushing up to stop that rotating? Can you see it's pulling down? So the answer we get for BY will be a negative answer. For this to be in equilibrium, if I say now, let's do it first, forces in the x direction, that's an easy one. All the forces in the x direction equal 0. It's not moving sideways, Bx therefore equals 0. All the forces in the y direction equal 0. People say, what do I do at the moment? It's not a force in the y direction, so it doesn't enter the equation. AY plus BY equals 0. At this point, 5% of you for some reason then say, well, therefore AY and BY equals 0. You can't say that. What you can say is AY is equal to net minus BY. They are equal and opposing forces. So let's take moments now. I usually always take moments at the left-hand support. It doesn't matter where you take moments. You could take moments on the moon. You would find it very difficult to work out perpendicular distance, but you can take moments wherever you want. It doesn't matter. So in this system here, I'm basically asking you the same question I asked you earlier. You know how I said, is it in equilibrium? Now I will say to you, it is in equilibrium. I don't know why I can't write neatly on that top right corner. So to make this system of forces in equilibrium, if that's a moment 75 kilonewton metre, what are the two reactions equal to? Well, let's take moments at A and work it out. Taking moments at A, I have a moment. It's going clockwise, so it's minus 75. A moment is a moment. We don't multiply it by distance. It's just minus 75. And then we come, does Bx cause a moment? No, because you can trace it back to the point. We just have By, force, distance is 10. The way I've drawn it, it's anti-clockwise. That equals 0. So By, now we know equals 7.5 kilonewton. And then from our previous expression, AY is equal to minus. Oh, hang on, which way? Oh, yeah, I got them around the wrong way. Did I confuse everyone? Sorry, you should have said something. I did that on purpose to see if you were concentrating. Okay, I lied. If ever I do something that doesn't make sense, say, Lizzie, I think you got it. Call out, Lizzie, I think you got it wrong. But now, you see, you all understand that because I made a mistake. Okay, we'll stop there and we'll continue on Wednesday. That's rotating that way. So this force must be pulling down.